Welcome back to 3 Inquisitive Kids. In this video, we will be learning about mixed operations with roots. So this is actually our last lesson of the chapter, and in the previous lessons we learned about irrational numbers, and then we learned about square and cube roots. Then we learned estimating and then real numbers. So now we're going to put all what we learned into calculating actual examples and expressions. Our learning goals for today is to master the algorithm of simplifying quadratic radicals. And we're going to master the application of what we learned onto problems. The upper and lower bases of a trapezoid are each 2 and the arithmetic square root of 2 centimeters and 4 arithmetic square root of 3 centimeters long. If it has a height of the arithmetic square root of 6 centimeters, what is its area? First, we have to know what is the formula to calculating the area of a trapezoid. The formula to calculating the area of a trapezoid is 1/2 times the sum of its two bases, a plus b, times its height. And now, since we know what the formula is, we can just plug in the values. You can see here that we've written out the formula and then replaced the variables with their given values. And then first we distributed this 1/2 into the parentheses. And we are left with the arithmetic square root of 2 plus 2 times the arithmetic square root of 3 times the arithmetic square root of 6. And then after that we apply the distributive property of multiplication again to get the arithmetic square root of 2 times 6 plus 2 times the arithmetic square root of 3 times 6. And then you simplify each term into its most simplified radical form to get 2 times the arithmetic square root of 3 plus 6 times the arithmetic square root of 2. And our answer would be that, and you have to write the label, which is centimeters squared. How do you multiply monomials and polynomials together? And how would you multiply a polynomial by a polynomial? This is some review. If we're going to multiply a monomial and a polynomial together, we're going to use the distributive property of multiplication to get rid of the parentheses. And it's the same thing for a polynomial. We are breaking it down into 2 smaller steps, also using the distributive property of multiplication. It's just that when we're multiplying a polynomial by a polynomial, we apply the distributive property of multiplication 2 times. How do you divide a polynomial by a monomial? It's the same thing. We still use the distributive property. Divided by m is the same thing as multiply 1 over m. And now, since we have multiplication, we can use the distributive property. So again, we turn this polynomial times monomial, and we break it down into monomial times monomial using the distributive property of multiplication. Can we use this basic method of multiplication to help us when simplifying quadratic radicals? Basically what we're going to do in this lesson is to combine what we learned about multiplying polynomials and monomials together, and also combining what we learned with the laws of exponents and quadratic radicals. Mixed operations with roots. Now try multiplying and dividing polynomials and monomials together with the addition of quadratic radicals. Here are some examples. Simplify these 2 expressions. Again, we can see that this is essentially a polynomial times a monomial. It's just that the terms are actually arithmetic square roots. For the first one, we use the distributive property of multiplication, and we are left with 4 times the arithmetic square root of 3 plus 3 times the arithmetic square root of 2. And that cannot be simplified any further, so that is our final answer. For the second expression, it's the same thing, except that in this case, it's division. We divide, and we are left with 2 minus 3 over 2 times the arithmetic square root of 3. Here's our third example. This time it's a polynomial times a polynomial. Here's a solution. Our first step in solving this problem is we're going to look at one of these expressions as a whole, and we're going to distribute that into the second polynomial. So here we have the arithmetic square root of 2 plus 3 times this first term of the second polynomial, plus we have a negative 5 times the arithmetic square root of 2 plus 3. This is the whole we're going to be distributing. And then we can see that we have a polynomial times a monomial plus a monomial times a polynomial. And now we're going to apply the distributive property of multiplication again. And so the first half of the polynomial would look like this. Minus 5 times the arithmetic square root of 2 minus 15. And this is how we got us to this step of the solution. You can see that this term and this term are actually like terms. You can view the arithmetic square root of 2 as the variable part of the term. You combine like terms to get negative 2 times the arithmetic square root of 2. In here, we have the square and the exponent canceling each other out. So we're left with 2 minus 15, which gives us negative 13. And so this is our final answer. And let me erase my ink so we can see what this says. This problem uses the following formula. X plus a times x plus b equals x squared plus the sum of a and b times x plus ab. If you want to, you can try to memorize this. And later on, when you're solving a polynomial times a polynomial like this, you can just apply the following formula. What's special about this is that you can see one of the two terms are the same. So that's going to be how you're going to be able to use this formula. All you have to do is first identify what types of expressions are being multiplied. Is it polynomial times monomial? Is it monomial times monomial? Is it polynomial divided by monomial? Or is it polynomial times polynomial? Then you just apply the distributive property of multiplication and then combine like terms. And if you ever come across a polynomial times a polynomial like this ever again, you can use this formula. And also, the good thing about formulas is that you have to notice that there is a equation. There's an equal sign over here, which means it's not just reading from the left side to the right. This equation is also true or valid if you read it from the right to the left. So sometimes when you're doing a harder problem, you have to think a bit more flexibly and see if I can reverse this formula to make calculating easier. Here's a changed up problem. Simplify these two expressions. The solution to number 1 is we're going to use the distributive property of multiplication, and we do that, we get the arithmetic square root of 6 minus 3. And we simplify this arithmetic square root of 27 into 3 times the arithmetic square root of 3. We subtract that, and for the absolute value, they did something here to get rid of the absolute value signs. We know that no matter what, we don't even have to actually calculate this. The arithmetic square root of 6 will always be less than 3. Why? 3 times 3 would be 9, and 2 times 2 is 4. And 6 must be somewhere in between that, because 6 is in between 4 and 9. So no matter what, the arithmetic square root of 6 must be less than 3. And since we are using absolute values over here, the result of an absolute value has to be positive. So if you already know that the difference of this would be negative, then you get to swap the order of the terms around and get rid of the absolute value. So that's why we swap this 3 to the beginning over here, and we swap this arithmetic square root of 6 to the end, and we keep that subtraction sign in between. But now, since we swap the orders, we can just get rid of the absolute value sign. But if you know that the value inside this absolute value is already positive, you don't have to change the order. You can just get rid of the absolute value. We later combine like terms to get negative 3 times the arithmetic square root of 3. For number 2, we have 1, because if the exponent is 0, then it's always going to be a 1. Plus, they kind of skipped a step over here. They turned this arithmetic square root of 12 into 2 times the arithmetic square root of 3. And since 3 minus 2 times the arithmetic square root of 3 is negative, we have to swap the order of the terms around, keep the negative sign in the middle, get rid of the absolute value signs, and that's how we're left with 2 times the arithmetic square root of 3 minus 3. And then we simplify the last term to get minus the arithmetic square root of 3. We combine like terms to get the arithmetic square root of 3 minus 2. Just like parentheses and brackets, when you come across an absolute value, you first simplify that. Remember that an absolute value should never be negative. Notice how over here it said the absolute value should never be negative. Does it mean that it has to be positive? No, because our friend 0 is right in the middle, and an absolute value can also be 0. So remember, if the sum of the terms inside the absolute value, you know it's going to be negative, you swap the order of the terms around, and you get rid of the absolute value. Now I want you to pause the video and simplify these 3 expressions. For the first one, we have the arithmetic square root of 3/2 minus the arithmetic square root of 2/3. What they did here is that they multiplied a 2 over 2 to the first term, and then a 3 over 3 to the second term, and you'll see why in a second. And they did this so after they simplified, they would get 1/2 times the arithmetic square root of 6 minus 1/3 times the arithmetic square root of 6. And you can see that they are like terms. They multiply that 2 over 2 and 3 over 3 on purpose so they can get like terms. And this is much easier to calculate compared to this first expression. We subtract and we are left with 1/6 times the arithmetic square root of 6. For the second problem, we have the arithmetic square root of 18 minus the arithmetic square root of 8 plus the arithmetic square root of 1 over 8. Let me clear all ink on this slide for a moment. We turn this 18 into 3 squared times 2. We turn this 8 into 2 squared times 2. And we turn this 1/8 into 2 over 16. You simplify and you get 3 times the arithmetic square root of 2 minus 2 times the arithmetic square root of 2. And they turn this 1/8 into 2/16 because they know that 16 is a perfect square number. And 2/16 is the same thing as 1/8, except that they turn the denominator into a perfect square number, so it will be easier to calculate. And now after they did that, they got like terms and they combined it to get 5 over 4 times the arithmetic square root of 2. Here's the first method into solving our third example. We have the difference of the arithmetic square root of 24 and the arithmetic square root of 1/6 divided by the arithmetic square root of 3. Again, we are using what we learned before. We are going to apply the distributive property of multiplication. In this case, it's used as division. We're left with the arithmetic square root of 8 minus the arithmetic square root of 1 over 6 times 3. We're going to break this 8 down into a 4 times 2. And we're going to multiply 2 over 2 to the second term. Take the arithmetic square root of both terms to get 2 times the arithmetic square root of 2 minus 1/6 times the arithmetic square root of 2. You combine like terms to get 11 over 6 times the arithmetic square root of 2. Over here they multiplied a 2 over 2 to the second term because they wanted to get a perfect square for the denominator. Do you have any other ways of solving this problem? Here's method 2 for solving this expression. Instead of first using the distributive property of multiplication, we first simplify what is inside the parentheses. We turn this 24 into a 4 times 6, and we turn this 1/6 into a 1 times 6 over 6 times 6. We multiply the 6 over 6 to the top and bottom. We simplify this first term up to get 2 times the arithmetic square root of 6. And we take the arithmetic square root of this fraction to get the arithmetic square root of 6 over 6. And we multiplied a arithmetic square root of 3 over arithmetic square root of 3 to this 1 over arithmetic square root of 3. So we can get rid of the square root on the denominator. And then you can see that we have 2 like terms inside the parentheses. We combine that to get 11 times the arithmetic square root of 6 over 6 times the arithmetic square root of 3 over 3. Simplify to get 11 times the arithmetic square root of 2 over 6. And here is a fourth expression. I want you to pause the video and see if you can calculate this. Our solution for this fourth problem is to first multiply a 2 over 2 to the first term, and then we broke this 18 down into a 9 times 2. You can see that by multiplying this 2 over 2, we're left with a perfect square on the denominator. We take the square root of the resulting fraction to get 5/2 times the arithmetic square root of 2. We still leave the arithmetic square root of 99 as it is, and we simplified this arithmetic square root of 18 into a 3 times the arithmetic square root of 2. We combine like terms, this term and this term, to get 1/2 times the arithmetic square root of 2 plus the arithmetic square root of 99. Can we simplify this any further? Well, it says that if a radical is not like terms with any of the other terms, it doesn't have to be simplified anymore into its most simplified radical form. If you want to, you can turn this arithmetic square root of 99 into 3 times the arithmetic square root of 11. Or if you want to, you could just leave it as it is. And this is our final answer. How would you simplify this expression? And we are given that a equals 3 and b equals 2. What was your method of solving this? We have multiple methods. Method 1 is to first substitute the values into the expression. We have the arithmetic square root of 1/3 minus the arithmetic square root of 2 times the arithmetic square root of 3 times 2. We use the distributive property of multiplication, and we simplify to get the arithmetic square root of 2 minus 2 times the arithmetic square root of 3. Method 2 is to first simplify the expression. We first use the distributive property of multiplication. We can see that this a and this a cancels each other out, so we're left with the arithmetic square root of b. Now we have a b times b inside the radical, so we are left with b times the remaining a, which is the arithmetic square root of a. And now this cannot be simplified any further. All we have to do is replace the variables with the numbers to get the final answer. The arithmetic square root of 2 minus 2 times the arithmetic square root of 3. Which method was more efficient? In the first method, when you first substituted the values into the expression, You had to do all this unnecessary calculating, and then in the end, you are left with the answer. But in method 2, we don't even have to worry about what the values are. We just did a lot of canceling things out and simplifying. In the end, we didn't have to do any calculation with the numbers. All we had to do is replace these variables with their values, and it was that simple. We got the same answer. The first method is to first substitute, then simplify, and the second method is to first simplify, then substitute. When simplifying mixed operations with quadratic radicals, it can be very troublesome or very hard to substitute the values first thing. First simplify the expression into its most simple form, then substitute the given values into the variables. We are given that a equals this and b equals this. Find the value of the arithmetic square root of a squared plus b squared plus 2. First simplify the algebraic expression using the formulas we've learned. This is a formula that you can use, which is a squared plus b squared equals the sum of a and b squared minus 2ab. So how can we use this to simplify this expression? First, we know that a equals 1 over the arithmetic square root of 5 minus 2. Now what we're going to do is we're going to multiply the arithmetic square root of 5 plus 2 onto this fraction. And we're doing that because we know that the denominator will get canceled into a 1. So we're just left with the arithmetic square root of 5 plus 2. We do the same thing for b, except this time it's the arithmetic square root of 5 minus 2. We multiply that on the top and bottom, and we're left with the arithmetic square root of 5 minus 2. Now we can start using this formula. A plus b would equal 2 times the arithmetic square root of 5, and ab would equal 1. You substitute that into this formula to get 2 times the arithmetic square root of 5. As shown in the figure, the side length of a small square is 1. Find the area of trapezoid ABCD. What was the methods you thought of? Now we're going to dive into a little bit more about application of quadratic radicals. In the previous practice problems, we learned how to simplify expressions, but now we're going to apply this into geometry and other types of math problems. There are multiple methods to do this as well. Method 1, we call it segmentation. Trapezoid ABCD can be divided up into 2 triangles and a smaller trapezoid, as shown in the figure. So now we have S1, S2, and S3. We have 3 different areas to calculate, and then add them all together when we're done calculating. The area of trapezoid ABCD is equal to these 3 smaller shapes combined. So now we're going to apply the formulas of how to calculate these shapes. For S1, which is this small triangle up here, we have 1 as a height and 3 as a base. So it's 1/2 times 3 times 1. For the second triangle, we have 3 units as the base, and its height is 2 units tall. So we would calculate it as 1/2 times 3 times 2. And for the smaller trapezoid, we have 1/2 times both of its bases added together, 3 and 6, and then times its height, which is a 3. Then we're going to add all these areas together to get 18. So that was segmentation. You can see that we broke it down into smaller parts with heights and bases we can actually calculate easily with. Method 2 is what we call the repair method. Here we are kind of thinking outside the box. We have extended some of these sides to make trapezoid ABCD into a bigger trapezoid, but you can see that this bigger trapezoid has a height and base that we can actually calculate easily with. So now all we have to do is calculate the area of this bigger trapezoid, and then we're going to subtract these small triangles from it. So this bigger trapezoid would be 1/2 times the sum of 2 and 7, which are its bases, times 5, which is its height. And then we're going to subtract S1 from it, which is 1/2 times 1 times 1, and then we're going to subtract S2 from it as well, 1/2 times 4 times 2. We simplify and we still get 18. And method 3 is the direct method. So here, we're just going to calculate the area of this trapezoid without doing anything else. The height would be DE, and trapezoid ABCD would equal 1/2 times both of its bases, CD plus AB, times DE, which is its height. Now we're going to substitute the values in. It would be 1/2. CD is the arithmetic square root of 2, plus AB, which is 5 times the arithmetic square root of 2, times DE, which is 3 times the arithmetic square root of 2. If you're wondering how they got these values, they actually used the Pythagorean theorem to help them figure this out. A squared plus B squared equals C squared. And you can see that there are a lot of ways you can use the Pythagorean theorem over here because there are a lot of small right triangles. We use the distributive property of multiplication, then we combine like terms to get 18. The quadratic radicals were used in the direct method to help us figure this out. So this is where quadratic radicals might come in handy because sometimes you just have to use the direct method and you're going to need to figure out the lengths of some of these diagonal lines that the problem doesn't tell you. Teacher's Appreciation Day is coming up. Combin, Karen, and Kaylee are going to make 2 separate cards for the teacher. One is 288 square meters, and the other one is 338 square meters. They have a piece of red ribbon to decorate the borders of both cards. Right now, they have 1.5 meters of ribbon. Is there enough ribbon for both cards? I want you to pause the video and see if you can figure this out. Again, we can use quadratic radicals to help us out. First, we know that these are squares, so that's where square roots and arithmetic square roots will come in handy. This is the side length of the first card, and this is the side length of the second card. Since a square has 4 sides, we're going to times 4 to it. First, we simplify these 2 arithmetic square roots into its most simplified radical form, which is 12 times the arithmetic square root of 2 plus 13 times the arithmetic square root of 2. Then we can see that we have like terms inside the parentheses. We combine that to get 4 times 25 times the arithmetic square root of 2, which is about 141.4 meters. And we have a total of 150 centimeters of ribbon. In the problem, they said it as 1.5 meters, but this is the same thing as 150 centimeters. So don't get confused on that. And since we know that 150 is greater than 141.4, then they do have enough ribbon for both cards. So here's our class summary. Today we learned about mixed operations with quadratic radicals. The formulas we're going to use later on with these operations would be a plus b times a minus b equals a squared minus b squared. That is a square difference formula. And this formula is the perfect square formula. The sum of ab squared equals a squared plus 2ab plus b squared. And again, this is the same thing, the perfect square formula, except that this time it's a negative sign instead of a positive sign. And this is a formula that you can use to simplify polynomial times polynomial if one of the terms are the same. So you would get x squared plus the sum of ab times x plus ab. We learn to first simplify, then substitute if we have given values. And for those geometry problems, we have 3 different ways to solve them: segmentation, the repair method, and the direct method. I hope you enjoyed this video, and I hope you learned something from this video. Thank you for watching, and we'll see you in the next chapter.